Hello everyone, we are now going to begin our lecture on a special type of variable called the discrete random variables. Now discrete, as you know, refers to a type of quantitative measure, right? So discrete values are countable values and they are represented as integer values starting from 0 and upwards. We are also going to learn how to calculate probabilities of discrete random variables and discrete random variable frequencies, right? So these are the topics that we are going to cover. The first one is discrete random variables, its definition, what it means, the notation we use for discrete random variables, and so on. And then we are going to learn how to calculate probability and how to represent probability distributions. And of course, after that, we are going to learn how to calculate the mean and the standard deviation of discrete random variables. And we will go through an example in this lecture. And I will show you step by step how we go about the calculations on discrete random variables. We'll also uh, do a worksheet on this as well. So I will post that video also, but that's separate from the lecture, right? What is random variable and a discrete random variable? So by definition, a random variable is a quantitative variable. Therefore, quantitative suggests it's going to be a numerical value. The variable is going to have a numerical value. It's a quantitative variable whose value depends on chance. So as we know, the word random means disorderly. There's no order, there's no pattern. It completely depends on chance. It cannot be predicted. Right? Nobody can say what value it can take, right? So that's what a random variable is. A discrete random variable is a random variable whose possible values can be listed. So it's the same definition that the word discrete has. Discrete means it's a numerical value that can be counted, correct? So a discrete random variable means the variable will have values which will come randomly, but it will also be a, a countable value. That means it will be a whole number, perhaps starting from 0 and then going up, going higher. Now, in particular, a random variable with only a finite number of possible values is a discrete random variable. And usually in the examples, we will note that the value of a discrete random variable is will not be a very large value, right? We rarely see values which are 1,000 or 50,000, right? It's a finite number of possible values, and normally it can be large values, but normally the values aren't too large, right? Let's look at how we can represent discrete random variables in notation form. Now, uppercase letters are used to denote a random variable, for example, x or y. And let x denote the random variable, example, number of siblings of a person. All right, so if we are talking about the number of siblings of a person or number of cars in a household or number of TVs in a household, that would be considered a random variable, and we would express that variable with the uppercase X or Y or any other alphabetical value, but is generally denoted in uppercase, right? Now, lowercase letters are used to denote the specific value of the variable, for example, x or y. So this is how we normally write or express uh, discrete random variables, right? We use curly brackets to represent an event. We use curly brackets, and within the brackets, we indicate the variable by the uppercase letter X or Y sometimes, or it can be any other letter, but it has to be uppercase, and then equal sign, and then maybe a small x, lowercase x, but it is the same letter as we use for the variable. So on the left hand side, the uppercase value represents the variable. It will not have a number on the left hand side. On the right hand side, it will be a numerical discrete quantitative value represented by x. So this lowercase x can hold or can be any discrete value. So events are denoted as, within parentheses, x equals small x. Therefore, the event that a person has two siblings is denoted as, you see over here within parentheses, we have the uppercase x, which represents the number of siblings, and then the equal sign, and then if the number of siblings somebody has is 2, then we just write 2 on the right hand side of the equal sign. Now, probability of an event is denoted as P. So it's the same notation, but we just put a P, and P indicates that the probability that the number of siblings, for example, equals 2. What is the probability that the number of siblings equal to 1? What is the probability that the number of siblings equal 0? All right. So this is how we are going to denote uh, the uh, the notation of discrete random variables. Now, sometimes you'll just, instead of the curly brackets for probability, sometimes we just use a round bracket and write it as x equals x. That is all right as well. All right. So probability of an event is denoted as P, and then parenthesis x equals x. Therefore, the probability that the random variable x will equal 2 siblings is denoted as P, and then within curly brackets or parenthesis x equals 2. All right. So if you don't have the P, then it refers to an event. If you have the P, then you're referring to a probability value, right? Now here is an example to work on discrete random variable. It's on color TVs. Following is a probability distribution for the number of color TVs Y owned by a randomly selected household with annual income between $15,000 to $30,000. All right, so that's what the study is on. It's just uh, the survey probably just went around asking in different households how many TVs, color TVs you have, and the response was a discrete value, either 0 or 1 or 2 or 3 or 4 or 5, right? So here, look at the way they have created the table to represent the discrete random variable. All right, they have Y here with number values 0, 1, 2, 3, 4, 5. So these are the possible values, the number of televisions in a household. And in the bottom row, just below that, they have probability that Y, uppercase Y, equals a particular Y value. So the probability of Y equals 0 is 0.009. Now they have already calculated the probability values for us. Pretty soon we are going to learn how to calculate the probabilities, but we are going to use the same formula for probabilities that we've used before, which is F over N. But for this exercise, they have already calculated the probabilities. So the probability that you have a household with 0 TVs is pretty low, 0.009. The probability that a household has 1 TV is 0.376. Probability that a household has 2 TVs is 0.371. Probability that the household has 5 TVs is 0.016. So these are the probability values. Right? Now the question here says represent the following in random variable notation. So this is an exercise to practice the notation of discrete random variables. So a household owns at least one color TV. Now over here, this is an event, all right? So it doesn't say anything about probability, but I will also include probability later on. But let's just represent this just as an event, all right? So for event, we don't need the letter P, correct? All we need is uh, a bracket like this, all right? Like this. Oops, sorry. Let me do a better job with the bracket. All right. And then y is the variable we are using, so it's y. Now, at least one color TV. It's when we use the word at least, we cannot just say y equals 1. All right? At least means more than 1. All right? It includes more than 1. So try to think how we can represent the word at least mathematically. All right? When we say that, when we say at least, I want at least one of something, right? What does it mean? That means the minimum number I want of a certain thing is 1. It could be more. All right? It could be 1 or more. That means y is greater or equal to 1. Correct? So that's how we have to represent this. We have to write it as y greater or equal to 1. So when we use the term at least or the phrase at least, we mean that I want I do want one item of whatever we are referring to, colored TV, but I'll be happy if you give me more, right? That's what the word at least means, one or more. Okay, so y greater or equal to 1. Next, it says exactly 2 color TVs. Now, this is easy because it says exactly. The way we are going to write this is y. Now, exactly means equals. So, equals 2. So, it's the event that we have exactly 2 TVs in a household. The one before that, at least one colored TV, said the event that a household will have one or more TV, therefore greater or equal to 1. Now, what does the next one say? It says between 1 and 3 inclusive colored TVs. So the way we are going to write that one is, it has to be, again, curly brackets, and then that means y is a value between 1 and 3 inclusive. It could be 1, it could be 2, it could be 3. That's what between 1 and 3 inclusive means. So the way we write it is 1. So y is a value less or equal to y. All right. Or rather, sorry, y is a value greater or equal to 1, right? Or we can say it as 1 less or equal to y. 1 less or equal to y is the same thing as saying y is greater or equal to 1, correct? And then we go y less or equal to 3. That means y is a value between 1 and 3, and this equal sign in the notation means 1 is included. It can be 1, it can be 2, it can be 3, right? So So that's how we represent or write in notation form between 1 and 3 colored TVs in this case. An odd number of TVs. Now, for this, uh, we'll have to include a lot of y values. So the way it's going to go is y equals, now what is an odd value here? 1 is odd, 3 is odd, and 5 is odd. So all three would be in our event. So y equals 1 or y equals 3 or y equals 5. Okay, so that's how we represent the event, y equals 1 or y equals 3. Now, if they said an even number of TVs, then you would go y equals 0, y equals 2, y equals 4. Okay, now let's look at the probability values, even though they haven't asked it, but let's do that right here. Okay, so what is the probability of at least one color TV? So that means probability of, now greater or equal to 1 means probability of one colored TV plus probability of 2 color plus probability of 3 plus probability of 4 plus probability of 5. All right, so that means you have to add up 0.376 plus 0.371 plus 0.167 plus 0.061 plus 0.016. Remember, the special addition rule is what we are applying. Probability of 1 or probability of 2, we have to add, correct? So you just have to take all the probabilities from 1 through 5, add them, and that's the probability of at least one colored TV. Conversely, we can also use, instead of adding up so many probabilities, we could use what was called the complementation rule. That means 1 minus not at least one colored TV. Remember the complementation rule, which kind of made our calculations easier. Instead of adding so many values, all we do is subtract the not value, the one that does not fall in our list, in our set, subtract it from 1. You should get the same answer. If you do 1 minus probability of 0, which is 1 minus 0.009, that should equal to whatever you would get by adding all these 5 probabilities here. Okay? Now, exactly 2 color TVs would be probability of y equals 2, which is just this value, 0.371. All right, so I'm just giving you a lead into this. We will do more problems in worksheets on calculating probabilities in different ways, but this is just an introduction at this point. Now, between 1 and 3 inclusive, that means the probability of y being 1 or 2 or 3. So what do you have to add up here? 1.376 plus 0.371 plus 0.167. So for this question, you're adding up probability of 1 plus probability of 2 plus probability of 3, which is going to be which value? 0.376 plus 0.371 plus 0.167, whatever that adds up to. All right, and then for odd number of TVs, again, it's the same special addition rule. You have to add up the probabilities of these events. Y equals 1 is 0.376 plus y equals 3 is 0.167 plus y equals 5 is 0.016, whatever those three values add up to will be your probability that an odd number of TVs gets selected or shows up. All right, so this is how we represent in notation form discrete random variable as well as calculate the probabilities. Now, once we find the probabilities, we can represent them. And in fact, we write all the probability values as a distribution. All right. So what we saw in the previous slide when we listed the probabilities of different events of colored TVs in a household. So it started with 0, 1, 2, 3, 4, 5, and we calculated and showed on a table all the probability values that represents a probability distribution. So probability distribution is a listing of the possible values and the corresponding probabilities of a discrete random variable or a formula for the probabilities. All right. And probability histogram is a graphical representation of probability distribution. So a graph of the probability distribution that displays the possible values of a discrete random variable on the horizontal axis and the probabilities of those values on the vertical axis. The probability of each value is represented by a vertical bar whose height equals the probability. So it's the same thing as a relative frequency histogram, but when we are dealing with probability, we instead of writing relative frequency or instead of listing relative frequency values on the y-axis, we call them the probability distribution. All right, so that's what probability histogram is. And the process of the process of uh, drawing a histogram is the same as what we learned before for relative frequencies, right? Now, probability distributions, we said we can list them in a table. They are a list of the probability values for all possible uh, all possible all the discrete values, right? All possible values of a variable, but it can also be given to us in as a formula. All right, so keep that in mind. The formula means a formula with which we calculate the probabilities. Let's look at this example here on discrete random variable, which will help us to work on how to calculate the probabilities of discrete random variables. The study is about number of siblings reported by randomly selected students. So a number of students were randomly selected and they were given the question, how many siblings do you have? And these were the values they reported. See this column here with a lowercase x, it represents the values, the distinct values of the variable number of siblings, which is represented by the uppercase X. All right. So the number of siblings reported by the respondents, by the students, was between 0 and 5. So 0 being the lowest value and 5 being the highest value. And the frequency column tells us how many of the respondents reported a particular value. So 8 respondents said they had 0 siblings, meaning they were perhaps the only child. 17 responded 1 sibling, 11 2 siblings, and so on. All right. Now, the formula to calculate the probability is the same that we used previously, whether we are working on discrete random variable or any other kind of probability. We still use the F over N formula. So we have to first figure out what N is, and then we will have to uh, divide the F values by N. What is N? N represents the sample size or the total number of um, possible events from a trial. So when we are talking about probability, it would represent the total sample space. That would be n. Now, for this example, n would be the sum of all the frequency values, like we had studied before, right? When we were talking about creating frequency tables, we said n is the sum total of all the frequency values, and it's the same thing here. We will have to sum up all the frequency values in order to come up with a value for n. So 8 plus 17 plus 11 plus 3 plus 1 is 40. So that's what I'm going to write here. N equals, let me use a different color, n equals 40. All right, so this is what n is. Again, I just want to tell you that or point you to a common mistake that I find. N is not the sum of the x values. All right, be very careful about that. Be warned. N is not the sum of the values. It's always the sum of the frequency values. All right. So again, just because we have numbers in the first column, n is not 0 plus 1 plus 2. No. N is always the sum of the frequency values. And once we have figured out what n is, we have all these individual f values for the different x values. Just use this formula f over n. So the first probability of selecting somebody who said 0 siblings would be f over n. That would be 8 divided by 40. All right, which would be 0.200. 17 upon 40 would be for the next one. That would be 0.425. 0.425. Then the number reported 2 siblings. To find the probability of that would be 11 upon 40, and that would be 0.275. Then we have 3 on 40, which is 0.075, and then 1 upon 40, which is 0.025. 0.025, and finally 0 on 40 is 0, right? For 5 siblings, no one reported they had 5 siblings, so that's 0.000. And when you sum up the probabilities, they should give you something close to 1.000. All right, so that's how you calculate the probability values. Now, you can be the data can be presented to you in a vertical form. Over here, the list is written vertically, or in a horizontal table. All right, so you have all your x values across on the first top row, and then we have all the f values again laid out horizontally, and you can calculate your probability values. But this time again, you have to sum up all the f values. These 8 plus 17 plus 11 plus 3 plus 1 is going to be equals n. All right, n equals 40. All right, and then you do 8 over 40, 8 over 40, 17 over 40, same thing, right? But it's just a different layout, that's all that is. But I just wanted to present both the formats to you in case on the tests you see one of these formats. You will understand that it's the same process. All right, for n you are summing up all the f values, and then you are applying the formula f over n to calculate the probability values. Again, another thing I wanted you to remember is that for the probability values, even if you're doing 8 over 40, do not write it in fraction form. Please convert it to decimal form to the third decimal place. Do not round it up to the second decimal place, right? Now, once we find all the probability values for all different x values, we get what's called a probability distribution. And once we have a probability distribution, we can go ahead and create a probability histogram, right? And this histogram is the same as a relative frequency histogram. Just because we are dealing with probability now, we call it a probability histogram. So along the x-axis, we have all the unique values for the variables, in this case 0 to 4. They've skipped 5 because there wasn't any values for 5. So it's 0 to 4. And then on the x-axis, we represent the probability values. The highest probability value in the distribution is 0.425. So we've scaled the vertical axis up to 0.45, and then the rectangular bars, these rectangular bars for the histogram goes as high as the probability values for a particular x value. So for 0, it's 0.2. So this rectangle goes up as high as zero point 0.2. For 1, it's 0.425. So we have this rectangle go up between 0.4 and 0.45, which would be 0.425. So this is a histogram, a probability histogram, and it is created the same way as a relative histogram, relative frequency histogram was created. So when you are asked to create a probability histogram, please make sure you give it a proper title and label the axis, right? Now here is a stated rule about the sum of probabilities, and we've already stated this before, but let's go over it formally. The sum of the probabilities of a discrete random variable. So for any discrete random variable x, we have the sum of all the probability values must be equal to 1. Right? So sigma is sum, and probability values for discrete random variables is written as p, and then within brackets x, referring to the variable, equals whatever the different values of x would be. So once you find the probabilities and sum them up, you should come up with a value of 1. If it is anything else, not close to 1, I mean, sometimes because of rounding, you may not get exactly 1. You may end up with 0.998 or 0.999. That's fine, but it should be as close to 1 as possible. Now, this slide is about interpreting a probability distribution. So interpretation of a probability distribution states in a large number of independent observations of a random variable x, the proportion of times each possible value occurs will approximate the probability distribution of x, or equivalently, the proportion histogram will approximate the probability histogram for x. In other words, it's stating that the proportion of times a particular response will take place will be close to whatever the probability distribution is. All right. And that's not surprising, because the formula we use for probability distribution is the same as something we would use to calculate relative frequency, which is also called the proportion. All right, so that's what this states. The proportion is going to be close to the probability distribution of a particular, or for a particular value. All right, or equivalently, the proportion histogram will approximate the probability histogram for x. So that's true for not only the distribution, but also for the histogram we come up with for the particular data set, right? Now, these two graphs demonstrate what we just spoke about, the histograms of proportion and probability being almost the same, approximately the same. All right. So this study was for histogram, uh, or this study represents a histogram of proportions for the numbers of heads obtained in 3 tosses of a balanced dime for 1,000 observations. Probability histograms for the number of heads obtained in 3 tosses of a balanced dime is what's shown in diagram B, and diagram A is for the proportion. As you can see from the y-axis label, it represents proportion, and probability is for the second diagram, and we see that the histograms are almost the same. All right, pretty much the same, except we see that for 2 it's a little bit lower than what we have in this second diagram. So the bottom line is they should be approximately the same. Now we learn how to calculate the mean of a discrete random variable. It's an easy formula, but we have to work this through a table. But let's see what the formula is first. So mean of a discrete random variable is the mean of a discrete random variable x is denoted as mu sub x, or when no confusion will arise, simply mu. It is defined by mu equals sigma x times p of x equals x. So what is p of x equals x? These are the probability values, right? These are the probability values. X represents the unique discrete values, correct? These are the x represents the all the like 0, 1, 2, 3, 4 that we had for the number of siblings. So x will represent the unique values for the random variable, and what we do is we take those values of x and multiply by their corresponding probability values, and then we sum them up, and that's going to be the mean, and that's all. All right, now there's no division by n. Remember, normally we say that mu has this formula sigma x over n, correct? Sigma x over n. Why aren't we dividing by n? Simply because we have already divided by n when we were calculating the probability. Again, probability was f divided by m. That was the formula for probability. So because that part was already done at the time of calculating the probabilities, we don't need to divide again by n. All we do is multiply the probability values by the respective x values and sum them up. And we'll work this through a table. Now, another name for the mean is the terms expected value and expectation are commonly used in place of the term mean. So when we are talking about or working with discrete random variables, sometimes instead of using the term mean, you will see the words expected value or expectation being used. That refers to the mean, right? As far as the interpretation of the mean of discrete random variables go, let's figure out how we go about interpreting. It says here, in a large number of independent observations of a random variable x, the average value of those observations will approximately equal the mean or mu of x. The larger the number of observations, the closer the average tends to be to mu. In other words, what it means is when we do a study, the average response from a study will will equal to whatever the mu or the mean calculated from all the values of X that were reported. So that means if we take a large number of independent observations, then we'll see that the value that is being reported on average more frequently will be equal to whatever the calculated mean would be from that data set. Now, as far as the standard deviation of a discrete random variable is concerned, there are two formulas given to us to calculate the standard deviation. One is the defining formula, which follows the definition of standard deviation. However, it is more involved in the sense it's more time consuming and less efficient than the computing formula. But we have two formulas. The first one, defining formula, is sigma equals square root over sigma x minus mu whole squared times the probability values. So here for the defining formula, what we have to do is we have to take all the x values and from them subtract the mean, which we should have already calculated before we get to the standard deviation. So we find those differences between the actual values and the mean and then square them and then multiply them by the probability values, the respective probability values, and then we sum them up and take the square root. So that's the defining formula. For the computing formula, we square all the x values and multiply them by their respective probability values and then sum them up, and then we subtract mean squared, mu squared, from the summed up x squared times probability values, and then we take the square root of that. All right, so if we work through an example, or when we work through an example, you will see that the computing formula is easier to use. There's only one step to it, rather than which is finding the x squared values and then multiplying by probability. Whereas for the defining formula, it's just a few extra steps. All right. I'm going to work through this example on calculating the mean of discrete random variables, and then in the next slide we'll work through calculating the standard deviation. So we are given a set of values here, this probability distribution table. We don't know what this data set refers to, but they've calculated the probability values. So now it's called a probability distribution. So based on this data, let's calculate what the mean is. Let's go through the process step by step. We have a table here with all the y values, the discrete random variable values given to us from 0 to 5, and these are the calculated probability values. So we have here the probability y equals y. So let's just copy down these probability values first. All right, so I'm going to write here, just list all the different probability values given to us: 0.009 for 0, 0.376, 0.371, 0.167, and 0.061, and then the last one is 0.016. Now in this column here, where we do y multiplied by each of these probability values, all we do is multiply the probability values by its respective y values, right? So for the first one, 0.009 times 0 is 0.000. Again, keep your values to the third decimal place. Next one, 0.376 times 1 is 0.376. 0.371 multiplied by 2 is 0.742. 0.742. Then we have 0.016 it's 0.167, right? 0.167 times 3 is 0.501. 501. And then what's the next one? 0.061 times 4, correct? That's 0.244, 0.244. And then the last one is 0.016 times 5, correct? So 0.016 times 5 is 0.080. So now that we got all these values, y times the probability values, we just have to sum up all the values in this column, and that would be our mean value. So we've taken here we've used y, so can replace x with y, and then probability of y equals y is what it should be. But generically, formulas are written with x in them, but you can translate the notations, all right? So to find mu, you have to do the summing part now. So I'm going to go and sum up all these values. So 6 plus 4, 10. So it's going to be 3 here, all right? So 1.943. So when we sum up the last values in the last column that we calculated by multiplying y values with their respective probability values, we get a sum total of 1.943, and that's what the mean is. So mu is equal to 1.943. That's the mu, which means that on an average, the reported value from this study for a large set of observations will be close to 1.943. That's how we interpret the mean, right? Now we are going to go through the process of calculating the standard deviation using the same example, same data set that we used to find the mean. All right, so the mean that we found before was 1.943. All right, so let me write that down before I forget what it was. Now, we are given here two formulas to calculate the standard deviation, but I'm going to use the computing formula because it's faster and it can be worked out using fewer columns than the defining formula. All right, so what is the defining formula? It's a sigma equals square root over sigma x squared times the probability values minus mu squared. All right, so the mu we already know is 1.943. We just have to square it when we apply the formula to find the deviation. However, this part, x squared times the probability and then summing it up, is what we have to work through this table. Now, we have the probability values. I already noted down the probability values from this table, the probability distribution table. So those are listed here. All we need to do is square up all the y values, and then in this final column we will multiply the probability values with the y squared values that will be listed in the second column. So 0 squared is 0. All right, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. All right, so now we have to go about multiplying the y squared values, with the probability values. So for the first one, anything times 0 is 0, so I'm going to write here 0, 0, 0, 0. For the next one, 1 times 0.376, so 0.376. Now the rest of the multiplication, let me just work this out and list all these values, but I guess you get the idea now. It's 4 times 0.371, 9 times 0.167, 16 times 0.061. So let me do these calculations uh, on the side, list them here, and I will come back. So all these values of y squared times the probability values are listed now. So we have to sum them up, and that should come to 4.739. All right, so when you sum up these values, it should be 4.739, and that's the value that we are going to plug in for this entire first term of this expression. So we're going to have the square root, all right, and then 4.739. That was calculated completely through this table by going step by step through this table, and then minus mu squared. All right, minus, now mu was 1.943, so let me square that here. 1.943 is 3.775. All right, so that's what we get, 3.775, and now you can complete the calculation. So we have square root over 0.964, which when we take the square root of gives us a value of 0.9818. We can round it off to 0.982. So that's the process of finding the standard deviation of discrete random variables, right?